Okay, it is very important concept of that is inverse Laplace transform. Now the figure indicates very clearly the relation between that transform and the inverse transform. In the t domain we have the function, in the s domain we have the transform. So L takes this input as f of t and gives the output as the transform f of s, and this particular situation is simply recorded in this way, that Laplace transform of f of t is that f of s, and f of s is called Laplace transform of this f of t, and L inverse is the inverse of this one. So it takes the s domain function, okay, s domain, and it returns in t domain. So what it does is it takes the transform and gives the inverse transform here. I mean to say that this particular f of t is called inverse Laplace transform of f of s. So from this equation, simple manipulation, that is algebraic adjustment, this L goes that side, it becomes L inverse of f of s and f of t remains. Now you can take the screenshot if you want it, and as a particular case, Laplace transform of e power 3t is 1 by s minus 3, and this is nothing but f of s. So this f of s, if we apply L inverse now, we'll get that back f of t, that is nothing but 3t, e power 3t. You can take the screenshot if you want it. Okay. Okay, let us see this problem. I have increased the complexity slightly here in term by term. Now as per the linearity property, you can separate it as 1 by s minus 2. Okay, first of all I am writing the problem, plus 5 by 7 s minus 8. Now if I separate it as per linearity property, what comes then? L inverse of 1 by s minus 2 plus 3 comes out, and L inverse of 1 by s minus 4, and then 5 comes out, 1 by 7s minus 8. But you know that we have 1 by s minus a as e to the power of 80. L inverse of 1 by s minus a as e to the power of 80. So it should be s here. You can adjust any constant here. So what I now do is I will take 7 out common. So I will write it here in this way, and I will make it as 8 by 7. Okay. So what I have done in this, I have just taken 7 out. So s minus 8 by 7. Now this will be e to the power of 2t plus 3 times of e to the power of 4t. Okay, otherwise I'll make a small change in the question. I'll make it as plus 4, so that it will be e to the power of minus 4t, and then this one plus 5 by 7 e to the power of minus 8 by 7, here it is. So it is plus 8 by 7t. Okay, this is the inverse Laplace transform for this function. You can take the screenshot if you want it. Okay, in this problem they are given separately the factors, individually the factors are given. Sometimes they will make it as one fraction and they give. For example, let us talk about that one. Find example number 2. Find L inverse of s by s square minus 3s plus 2. In this case, what we need to do here is, first of all, we have to break this into two first degree linear factors. Okay, so now s by s square minus 3s plus 2, there are two possibilities. This second degree function, the second degree polynomial, may be split it into, may be able to split into two first degree factors. Sometimes it is not possible, then irreducible factor we will do in the next problem. So here we know that it is very easily can be written as s minus 1 into s minus 2. Now we assume that it is a by s minus 1 plus b by s minus 2. I mean to say that s by s minus 1 into s minus 2, this one I am continuing in this way, implies s is equal to a times of s minus 2 plus b times of s minus 1. This is equation number 1. Now we need to find the values of a and b. Now you can make in this way, s is equal to a plus b times of s, and then the coefficient remaining constant is minus 2a minus b. If you compare the terms which are like terms, then a plus b must be equal to 1 and minus 2a minus b must be equal to 0. Comparing, we get a plus b is equal to 1 and minus 2a minus b is equal to 0. We have to solve these two to get the values of a and b. You take it up to here. Okay, solving these two, we get, just adding these two, minus b plus b gets cancelled, so minus a is equal to 1. Solving, we get minus a is equal to 1, implies a is equal to minus 1. Once we substitute minus 1 here, that goes that side, b becomes equal to 2 and b is equal to 2. You can cross verify, a is minus 1, b is 2, 2 minus 1 is 1, and minus 2 minus 1 is plus 2 minus 2 is 0. Okay, fine. Therefore, what comes now is, therefore s by s square minus 3s plus 2 is equal to minus 1 by s minus 1. I am just substituting the value of a and b. So plus 2 by s minus 2. So when we are able to break this here, then the next step is just to apply the inverse Laplace transform on both the sides. So what comes now, that as per linearity property, this gets separated, and hence we are getting this step, plus 2 out, L inverse 1 by s minus 2. So it is minus of e to the power of t plus 2 times of e to the power of 2t. This is the inverse Laplace transform for s by s square minus 3s plus 2. In case if we are unable to reduce this into first degree factors, then we will treat it as irreducible, and then we'll try to make up the perfect square and we'll separate the terms. That we'll do in the next problem. If you want, you can take the screenshot for this. Okay, now we are finding the inverse transform for this one. The denominator is s square plus 2s plus 3. If you look at this, the discriminant for this is 4 minus 4 into 1 into 3. That is negative, therefore it has no real factors of first degree, and hence it is irreducible. So what we now do is L inverse of s by s square plus 2s plus 3. So first of all, to find that inverse, I will make it in a suitable manner like this. S by, you try to make up the perfect square from this. It is like a square and it is like 2ab. It is a square, so 2a, b value is 1, so we need 1 square. Now, so that it becomes s plus 1 whole square, the leftover part to be written here, it is 1 square, so 1, so it is 2 now. Now I'll write it as s by s is s plus 1 whole square for this part, and plus this I'll write it as root 2 square. Now for this complete, we want L inverse, and L inverse comes for this one. Okay, so L inverse. Now if you look at this, it is looking like okay, you see s plus 1 is there, so we must have to use s plus 1 here. So what I'm now doing is I'm making the adjustment as s plus 1. So it is now s plus 1 whole square plus root 2 square. This complete with the L inverse. Now we will separate two parts from this one. One is for this part and one is for this part. Okay, you can take the screenshot now. Now you see that it is L inverse of s plus 1 by s plus 1 whole square plus root 2 square. This is one part separated, minus L inverse of 1 by s plus 1 whole square plus root 2 square. Now let us have a recall of the previously learned concept. That is, you know that L of sin AT will be A by this A by s square plus a square, and for cos AT it will be s by s square plus a square. Now when this comes this side, L inverse of this, so L inverse of this is this one. So if we have constant here, then sine will be the inverse. If we have s, we will be having cos as the inverse. But if it is s, it should be s here. If it is s plus 2 here, this is because, okay, I mean to say here s plus 2 whole square plus 4 square, for example. Then I want the inverse for this. So what I need to do? Then we'll go for first shifting theorem. Okay, so let's wait for some time. If it is e power at, then or else if I'll write it e power kt, then in the place of s we will be having s minus k. So it will be s minus k whole square. If we have here e to the power of kt, L of this will be in that way. Now if I remove this L here, L inverse will come, but the point is we need to, okay, I mean to say e power kt is there, then s minus k and s minus k will appear, s minus k whole square. So if I apply this one, so the extra part which comes is this one, or else I'll say in a simple way, if I have s square plus 1. Now this is actually the case when I am using sin t, Laplace transform of this one. If I have sin t with e to the power of 2t, this will become 1 by s minus 2 whole square plus 1. Okay, now if we have this one and we want the inverse of this, what we need to do is treating this as just 1 by s square plus 1. You first of all write the inverse for this one. The inverse is sin t, but because s is s minus 2, you multiply this with e to the power of 2t. I hope you understood. Now what you now do, okay, this is the background. If any problem, again come back to this one. Just feel that it is only s, then what comes here, s by, okay, s by s square plus root 2 square. Now it is looking like s by s square plus a square. Because it is s, it has to be cos at. A value is root 2, so it should be root 2t. But s is not s here, it is s plus 1. So it is because of the extra factor e to the power of minus t. I hope now you are very clear. Minus. Here s is missing, so constant should be there. Either s should be there or constant. If it is s plus 1, s plus 1 should be there. If it is s plus 5, s plus 5 should be there. Now when s is not there or s plus 1 is not there, their constant should be there. Constant is root 2 here, so root 2 should be there. So what I now do is 1 by root 2, and root 2 is available here. Once root 2 is available, it should be written as sine root 2t. But because it is s plus 1, we need to write as e to the power of minus t. So this is how we calculate the inverse of the inverse Laplace transforms of the functions. Okay, now when we are clear about the calculation of the inverse Laplace transform, the next important issue comes is solving the differential equations that we'll see in the next part. Okay, thank you. Ending this one.